All right, this is a parametric equations review for a calculus course, an integral calculus course. And so at some point in integral calculus, you're going to have to deal with parametric equations. And rather than talking about this in a classroom and wasting precious calculus time, it's much better to review this online so you can pause and rewind whatever you need to do. So what is a parametric equation? Well, to get mathy about it, a parametric equation is defined using the following definition. You have two functions, both functions of a parameter t, and if you let x equal the first function, f of t, and y equal the second function, g of t, where t is defined on some interval I, where those functions basically are defined on an interval I, then we would call x and y parametric equations with respect to a parameter t. And so t often can be thought of as time. You let time tick forward, and the path of the x values of the path are defined by the function f of t. And let me highlight that. And the y values of the path are defined by the function g of t. They're kind of a straightforward statement. However, to see it in action is better than to write it down. Before I show you this in action, let me just go ahead and show you or write down another definition of parametric curve, and then we'll go through and see this in action, what a parametric equation does. So parametric curve is a set of points, f of t, g of t, where t is a set of, an interval I. And these set of points follow a directed path that we're going to call a parametric curve. And a couple important statements here. That phrase, directed path, tells us something very unique about parametric curves. They actually carve themselves out with a specific direction in mind. So they will follow a path. We usually use arrows to denote that path. And then the parametric curve itself is a definition of the path that they follow. If the time values are allowed to be just between a and b, then f of a, g of a is called the initial point, and then f of b, g of b is called the terminal point. So those are really, and in fact I'll highlight those are really the only definitions we need to kind of get started. Now let's take a visual of what a parametric curve looks like. Probably the best visual of a parametric curve is an Etch-a-Sketch. In an Etch-a-Sketch, and I think I can actually draw on this. In an Etch-a-Sketch pen mode, this guy right here would be like the x-axis. You would control the x-axis, x of t, and this would control y of t. And so you're allowed, so each of these is a function. It's a function of time. So as time ticks on, you might move the x values to the right, then move them to the left. That's what that dial does. And the y values, so these are the x, the y values here, you can move up or down as you sketch it out. And while the curve itself that you're sketching is not a function necessarily in the traditional sense, each component, the x components and the y components, they are functions. So let's go ahead and just see what this looks like. Let me stop sketching. And you get this wonderful view. You can totally see this, actually pretty neat, right? So it is, yeah, this person's pretty amazing how they're doing this. Very sped up. I'm fascinated by this. Okay, but you can see that as a function, as a curve, that's not a function of x, nor is it a function of y. However, as a parametric curve, the functions x, which is equal to f of t, and the function y, which is equal to g of t, those are functions. So parametrically, this is a function, and this person is amazing. What they're doing here, it's pretty amazing. Now you could always sketch parametrics by hand, and that's actually what we're going to do. But I want to showcase kind of how to use technology first to get a good visual of parametrics. So I'm using WinPlot here, very free program. And when I go to equation, I can select parametric. That's not supposed to come up. And I'm just going to use the standard ones that are there. You can use whatever functions you want. It's just going to graph for me 3 cosine of 3t and 3 sine of 4t from 0 to 2 pi. And I'll make the pen width, pen width of 1 is fine. So there you go. Oops. And you can see right now that it is actually somewhat large. So I'm going to zoom out a little bit. And I'll do it a few more times. I don't have a keyboard hooked up, so I'm just going to go ahead and zoom out a couple more times here. And you can see, again, not a function in x, nor is it a function in y. However, as a parametric curve, the x values that were kind of being scraped out there and the y values that are being scraped out are functions of time. Okay, and then we can actually go ahead and learn how to do this. And I'm going to show more examples in the future, but for right now, I'll just do this. So taking a first example, let's go ahead and just sketch a parametric curve defined by x of t equals cosine of t, y of t equals sine of t. And we're going to indicate the direction of the path of travel for our particle along that curve. There are a couple, actually several ways to graph this, but I'm going to do the most basic method first, and then I'm going to get a little more complicated, then I'll get a little more advanced. The most basic method, the method that most people will do initially when they learn how to deal with parametric curves, is they'll make a table of values. So they'll have an input value like we normally would, but our input value here is t. We'll have an x value associated with that and a y value associated with that. So I know that cosine and sine have a period of 2 pi, so I can go ahead and throw some values in here. I'm not going to go through and do a ton of values. I'll just increment initially by pi over 4. So 0 and pi over 4 and pi over 2 and 3 pi over 4. But then once I get the idea of the path, I will then go just to go to pi, and then 3 pi over 2 and 2 pi. All right, I forgot my parenthesis there. So when t is equal to 0, we see that the cosine of 0, well, that's just going to be 1. In fact, I'll do all the cosines first. And when t is equal to pi over 4, cosine of pi over 4 is 1 over the square root of 2. Cosine of pi over 2 is 0. Cosine of 3 pi over 4 is a negative 1 over root 2. Cosine of pi is a negative 1, and cosine of 3 pi over 2 is 0, and 2 pi, again, is 1. And this is from your trig course. You should really be able to kind of hammer those out very quickly. Same thing with the y values here. So y of 0 is actually 0. Y of pi over 4 is 1 over the square root of 2. Y of pi over 2 is 1. Sorry, I'm saying y of, but I mean sine of. Sine of 3 pi over 4 is actually positive 1 over root 2. And then sine of pi is 0, and then negative 1 and 0. You can always get these from the graph of cosine and sine as well, but I'm avoiding that right now just because I'm going to use that in my second derivation of the method here. So let me go ahead and just move something out of the way here. I'm going to go ahead and graph the curve. So again, starting at time 0, and I'm going to go and call that a height, x value of 1. That's a y value of 1 and negative 1 and negative 1. Okay. So at time 0, the x value is 1, the y value is 0. So I'll plot that. I'll do that in blue, actually. 1, 0 is right here. And then at time pi over 4, we're at x equals 1 over root 2, y is equal to 1 over root 2. So it might be something like right there. Say 1 over root 2, comma 1 over root 2, so you can actually see that point. And by the way, that's time is equal to pi over 4. And then at time equals pi over 2, we have an x value of 0, y value of 1. So in this, I can kind of make the assumption it's carved out like this so far. In the direction of travel, I'm using little arrows. That's the travel that my particle is going through, my direction of travel. And of course, you can keep going here all the way around. I'm just sort of cheating. At time 3 pi over 4, the x value is a negative 1 over root 2, but the y value is still a positive 1 over root 2, so that matches. So again, we've done this, we've done this. Now we should be at negative 1, 0, which we are. And then it's going to continue this pattern. So by the time it gets to 3 pi over 2, it's at 0, comma negative 1. It's way down here. So it's just going to continue that circular path, carving it out this way, and then it'll finish the loop, you could see, by the time it gets to pi over 2. Okay, so for a full circuit from time 0 to time pi over 2, it's done a full circle for this. Now, that shouldn't be so surprising because the fact is these are circular functions, but still, this is our first basic introduction to parametric curves. There is actually another and kind of more interesting way to sketch parametric curves, so let me get set up for that. So here's the setup. I have basically a piece of paper with 4 set of axes on it, and I'll have one set, the upper right hand corner there, for y, and right below that I'll have for x. So the first one I'm going to graph is y equals sine of t. So if I just quickly sketch this out, nothing too crazy, just quick kind of sketch. The sine curve looks something like this, right? And of course it goes in both directions. Try to be somewhat accurate here, but it's difficult freehanding this. Okay, we know that's time pi. That'll be time 2 pi. This is the height of 1. This is the height of negative 1. Time pi over 2 and time 3 pi over 2. Excuse me. And then you could do the same thing for the cosine. The cosine starts high and goes low, goes back up high again. So let me do this. Something like that. Nothing too crazy here. That point right there is 2 pi. And this is pi. This is pi over 2. This is 3 pi over 2. Notice how I try to line them up perfectly. They're not perfectly lined up, but hey, it's still okay. Now, the y one I'm leaving alone because what I'm going to eventually graph is the function where it's x versus y, and I have these heights. This blue curve, y equals sine of t here, this gives me the heights of the function of the parametric curve at any given moment. However, the x equals cosine of t, that does not give me the x value. It does technically give me the x values at any given moment, but unfortunately, my x values are this axis and my time values are this axis. So again, with respect to when we're graphing y equals sine of t, the outputs are correct. The y values are the outputs. However, our x values for the x equals cosine of t, they're sort of wrong. You can see it in this picture right here. The x values, the x-axis should be the horizontal axis, not the vertical axis. So what I'm going to do is I'm going to move this or transpose this curve, this x versus t axis. I'm going to move it over to where the x-axis is the horizontal axis and the t-axis is the positive or the vertical axis. And to do that, you have to kind of tilt your head a little bit and visualize that we're grabbing this curve right here. And in fact, maybe I can do it. You can see I rotated it 90 degrees, but that's not enough because even though the x value or x-axis there is now horizontal, the t-axis is pointing in the wrong direction. I need t to go up positive. So let me go ahead and flip that. I'm going to go ahead and select this here again. Okay. So I finally got that figured out how to rotate around. Unfortunately, all my numbers look weird to you now because they're backwards and they're flipped. But the idea is that you're going to take that graph, flip it, you tilt the x-axis to the right, and then flip it vertically to where your t-axis points up. So if I go back a couple steps here, you can see that it originally looked like this. And so all I'm basically doing is saying, well, if time is going to go up and the x-axis is going out, it looks something like this. Oops, I'm going to use the wrong color here, but I'll use blue. Okay, it looks something like this. Not perfect, but... And I already have them listed there. This is time 2 pi. This is time pi, and so on and so forth. This is an output of 1 and an input of -1. What I'm going to do now is use these two curves. Let me highlight them. I'll use these two curves, the y curve and the x curve, if you will, to graph the final graph here. And the way I'll do that is say, okay, well, time is equal to 0. Notice the y value is 0, but the x value is 1. Again, when time is equal to 0, the y value is 0, and the x value is 1. That's when t is equal to 0. So I can read it directly from the graph. And then as time moves on to time pi over 2, the y values increase to a height of 1, so all my y values are going to go up. But the x values decrease as time starts to tick forward to pi over 2. The x values decrease to 0. So the y values are going up, but the x values are going to be moved over to the right, or left, sorry. So the y values are going to go up, but the x values are going to go to the right, left, again, sorry. So there's the path. The maximal y value is a 1, so I happen to know that's a 1. The maximal x value that we started at was a 1 as well. Now, if I continue from time pi over 2, let me use a different color just to showcase I'm going from time pi over 2, the y values start to decrease all the way down to 0. So they're going to go, the y values are going to go down. On the other hand, again, as I'm going to time pi, the x values continue to go negative. So the x values continue to go this way. So the y values are dropping, the x values are going to the left. So continue forward. The y values are dropping, but the x values continue over to the left. So by the time we get to y equals 0, we have something like this. This is the path we dragged out. We're at y equals 0, but x now is a negative 1. And you can see as time moves forward, ticks on and on and on, the x values start to go back to a value of 0. So as time ticks to time 3 pi over 2, the x values tend this way, and the y values tend to go all the way down to a negative 1. So they go down that way. So you're moving the curve to the right, but yet drawing still going down. So see that in action. It's going down, but it's moving to the right. So we have something like this. Again, the least y value is a negative 1, the minimum y value that is. And then finally, and I've already used red. I haven't used blue on these ones. So finally, as the time values tick forward to time pi, 2 pi, the y values increase, and the x values also increase. So the y values are moving up and the x values are moving to the right. So to showcase that, x and y values are both increasing. You have something like this. And there you have it. So that's a second way you can do this. And that's actually a more advanced, more conceptual way. And by the time you're in Calc 2, you should be able to do something like this. This is something I teach to my pre-calculus students. So you have two options. The worst way is to build a table of values because you can sometimes mess up. The second best way is this. If you can graph both what y is equal to and what x is equal to, and take that graph of x versus t, this graph right here, if you could take that graph and if you could rotate it 90 degrees clockwise so that your x-axis is the horizontal axis pointing in the correct direction, and then flip it vertically so your t-axis is pointing up, then you have the proper graph. Then you can start actually graphing this final graph of x versus y. So that's a second way you can graph. There is actually a third way. The third way you can graph a parametric equation is to use the relationship between the x and the y functions that were given to you. So let me go ahead and prep for that. So now we're asked to graph this same set of parametric equations via elimination of parameters. So we're going to eliminate the parameter or relate these two together. So if I see that x is equal to cosine and y is equal to sine, I want to create an equation involving cosine and sine. Basically I want to create an equation using like a theorem or an identity involving cosines and sines. And that would actually be the Pythagorean identity that cosine squared of an angle plus sine squared of the same exact angle is always equal to 1. If that's the case, well, since cosine is equal to x, that means that x squared plus, and since sine is equal to y squared, is equal to 1. That is my relation between x and y. It's not a function, it's a relation, but that is the equation of a circle of radius 1. So if I want to go ahead and now graph it, I can. I'll just do this. It's a circle of radius 1, so I'm just going to kind of chicken scratch out a circle here. I'm kind of doing a dashed line because it's hard for me to graph this out by hand, but here we go. So I have a circle, hopefully, of radius 1. Let's just pretend it is. -1, -1. All right. And the only thing that's missing when you do this, when you graph this using eliminating the parameters, in other words, rewriting a relationship between what cosine and sine is, and then getting x squared plus y squared is equal to 1. The only thing that you're missing when you're doing this is the direction of travel and your initial points and stuff like that. But if you can build a table very quickly, you can tell, again, very quickly, the direction of travel. So we've already built a table of values. Let me scroll up. Here's our table of values. Really, I wouldn't do such a big table at that point. I would just say, well, when time is 0, what's x and y? And maybe when time is pi over 2, what's x and y? So I could see the direction of travel. And that would just tell me that we started at 1, 0 right here, and we traveled this way. And you could check, again, by just throwing out 2 or 3 more values for time, that the whole circuit around is done in 2 pi, and it's traveling, the particle's traveling in that direction. So the very basic initial problem in graphing using, parametric curves, and you have 3 ways to do it. Now let's consider the second example. We're going to graph this set of parametric equations from t equals -2 to t equals +2. Something to note here is that, excuse me, of the 3 methods that we can use to graph, the building of the tables, building of the graphs, or eliminating a parameter, really building a table is always the easiest, but it's often the worst of the 3. In this case, building a table is actually going to be pretty advantageous. You just have to be very careful. So you can build a table of values again, but just to forewarn you, you have to be very, very careful when you do this, because if you take too large a jump in time, so let's say you plotted t equals -2, t equals let's say t equals -2, t equals 0, and t equals 2, you will not be able to see the pattern to this curve. However, if you do it like finely scaled steps, t equals -2 to 2 in half steps, let's say by 0.5, then you can get a very good idea of what these values are and what the curve looks like. And since everybody knows that I am a big fan of technology, I'm going to go ahead and use a little bit of technology here to help me out. So obviously that's what you're going to be using when you, if you create a fairly large table. So that's what I'm going to do here. You could also do this by hand, and there are some wonderful reasons why you would do that. But for now, let's just see what this looks like by using a table of values. So I'm going to hop over here to Excel, and I'll have time values here, and x of t there, and y of t there. And I'll say my time values start at -2, and then go to negative, let's just go in half steps, -1.5, and so on and so forth. And you can actually, if you select both those, you can drag that down. Unfortunately, I'm using a keyboard, so I'm not 100% sure. There it is. If you grab that lower right-hand corner, drag it down, it'll fill out the rest of the values for you. And now, hopping back over, x of t is e to the -t plus t. It's e to the negative time value plus time value. So I'm going to go back over here. This is equal to, you always have to start with that. It's equal to e, which is exp, raised to the negative time value plus the time value. Okay, so that's what we get there. Let me just double check that I did that. Yep, I sure did. I did that right. And now, instead of copying or typing that out every single time, you can go to the lower right hand corner, double click, and it'll automatically fill out all those values for the x positions. And then you can do the same thing with the y positions. Remember, the y is e to the t minus t. So let's go ahead and write in here again, equals exp for exponential of e to the time value, close that, minus the time value. Hit enter. And now I'll just double click the lower right hand corner to get the y values. So e to the negative t plus t and e to the t minus t. Yeah, okay, great. And so here's our table of values. I'll go ahead and pause the video while I copy and paste that. And now we can go ahead and just use this table to graph things out. So I'll go ahead and do that. Draw. Sorry, I'm speaking to myself when I say draw. And of course I'm using the wrong color, but that's okay. So when choosing the the scale for the axes, just pay attention to what the function outputs are going to be. And so I'll go ahead and let's see, the x values go from, they climb all the way to actually 5. So I'll go ahead and plot that in here. 1, 2, 3, 4, and 5. A little bit past 5, honestly. And they don't go negative. The y values don't go negative either, and they go all the way to 5s. 1, 2, 3, 4, 5. All right, so let's see. Time equals -2. We're a little bit past 5, comma 2.1. So I'm going to do this in red. A little bit past 5, comma 2.1, somewhere right about there. And then right around 3, comma 1.7. So x equals 3, y equals 1.7. Again, right around there. Oops. A little bit hard to get that in there. And then 1.7, comma 1.4. So 1.7, comma 1.4, maybe around here. And 1.1, 1.1. So this actually showcases something kind of interesting, that if you imagine this as a particle, between time -2 and time -1.5, it went this full first long distance. And then in the same amount of time, it went a shorter distance. And in the same amount of time, it goes to 1.1, comma 1.1, which is roughly right about here. Okay, so even shorter distance, and at time 0, it's actually at 1, 1. I should be actually showing that it's going kind of curving in. I can see that now. Looking over here, let's see, time 0, we're at 1, 1. Time 1, we're at time 0.5, we're at 1.1, comma 1.1, a little bit more in the y value than in the x value. So 1.1, 1.1. I'll do this in blue. It might be something like this. And then 1.36 and 1.7. So I'm going to say 1.4 in the x value, 1.7 in the y value. So somewhere around here. And let's see, time 1.5, we're at x equals 1.7, y equals 3. So x equals 1.7, y equals 3. We're probably right around here. It's the concavity of my curve wasn't perfect to begin with. And then finally, at time 2, we're at 2.1 and 5.3. So 2.1 and then way up at 5.3. Let's go ahead and do that somewhere around here. Something like this. So the concavity of my curve to begin with wasn't perfect. Sorry about that. So I just want to get that concavity in there properly. So I'm going to say it did look like this. If you're not too careful, you can get pretty bad curves. So it's not a function. You can easily tell it's not a function. However, we can easily see the path of travel for the particle. And we do have a table of values. It's actually not too terrible to create. You can create it by hand just by writing them out, or you can use computer or something like that. And then, let's see. Oh, and then the other major thing I want to talk about, again, I mentioned between time steps, your curve could slow down or speed up. So that's very important because that does happen. Curves do slow down and they do speed up. Oh, and actually, before I step away from this, notice I did not do what I did with the previous problems. I didn't eliminate the parameter here, nor did I draw a graph of y of t is equal to e to the t minus t, and then x of t equals e to the negative t plus t. Main reason why I didn't do the graph part of it, which is akin to this stuff right here from the previous example, the reason why I didn't do this style of graphing with the exponential functions is because our current example, this guy right here, is a mixture, both the x and y values are mixtures of exponential and algebraic functions. So graphing those by hand can be a terrible mess. So if that's the case, a table of values is often better. Also, eliminating the parameter here, there's just no easy way to do it. Sure, you could say, oh, you know what? E to the t is the same thing as y plus t. Okay, so great. Wherever I find an e to the t, I'll replace that with a y plus t. But that won't actually help out. That won't help out in the end. You might as well just leave it alone. It's no good. It's when it's obvious, you know, like the cosine and the sine that we had earlier. But when it's not so obvious, well, it's not so obvious. All right, so doing another example here. Now in this problem, I'm not going to tell you how to sketch this. I'm just going to say sketch it. You could build a table of values, or you could eliminate the parameter, or you could, technically speaking, do graphs. It's all your choice. However, this is actually pretty easy to see that the function x, which is equal to the square root of t, if you squared it, it'd become t. And I have a t here that I could sub in for. So this is where I know that I'm going to be able to use elimination of parameters, since, I'll write that out, since x squared is equal to t, since it's a bad word. My sister just yelled at me because of this. It's because, since it always has to refer to time. She is a journalist, so she gets on my case about that. Because x squared is equal to t, y is equal to 1 minus, well, it was t, but now we're going to replace that t with an x squared. So here we are dealing with the function y equals 1 minus x squared, and I could totally graph that. However, something to note, since the x values are equal to the square root of t, you know that the x values at minimum are going to be 0, and otherwise they'll always be positive. So a little note, and you should always do this if you can, a couple notes here. Note t is greater than or equal to 0 because you're taking the square root of it, so you're kind of stuck, which will also imply that x is greater than or equal to 0. So I'm only going to graph this curve for x values that are 0 or positive. Okay, so that should be okay. So what I'll do is I'll initially graph y equals 1 minus x squared, and then I'll erase where the time values are negative or where the x values are negative. So this is a good way to graph this. In fact, I could just keep that there. It's an upside down parabola lifted 1 unit. I'll just pretend as though that's 1 unit. So it looks something like this. Normally it looks something like that. In fact, I should not put an arrow at the end of that because that indicates a direction of travel. So that's what it normally looks like when you're drawing x versus y. However, as we've said, the x values here all have to be greater than or equal to 0. So I'm going to erase all the side here where the x values are negative. And now I'm going to go ahead and just test the direction of travel. So I'm going to say, okay, it doesn't really take very much to do this. You just t versus x versus y. When t is 0, x is 0, y is 1. So I'm going to use red to show that. X is 0, y is 1 is right there. When t is, let's just choose a nice number, 1, x is 1, y is 0. So by the time we get to time 1, we're right there, and so we can see we travel along this arc. Now, you want to make sure that it continues this path. The y values, as time goes on, you can see the y values are going to go very negative, right? As time goes to, let's say, 100, that's 1 minus 100, or in other words, the y value is negative 99. It actually will continue to fall, but it's always good to just take another value. So I'm going to let t equal 9, and I'm choosing 9 because I can take the square root of it. Then the x value is 3 and the y value is negative 8. So there we go. I know it's over 3 and down 8. I can easily see that's the path of travel. So elimination of parameters is very nice. Kind of a beautiful way to do this. Using the graphing method, or maybe I should say using a table, which is kind of what we did here as well, is okay if you capture everything. But it's very difficult to do that, as you've learned from algebra. It's very difficult to capture all information about a curve in a table. So that's why sometimes being able to eliminate the parameter helps out. Also, if I were to go back, let me scroll up a little bit, and try to do the graphing method, while I'm a huge fan of the graphing method, there are some weaknesses of it. And one of the weaknesses of that method is knowing how the curve gets shaped as time goes forward. So I don't know if I want to be brave and try it. I think I will, since I have time here. So what I'm going to do is on the upper right graph, I'm going to graph y equals 1 minus t, where this is the t-axis and this is the y-axis. 1 minus t, that's a line, right? That's decreasing, and it goes through 1, 0, 1. So let's go ahead and just showcase that. Okay. And here I'm going to graph in the lower right-hand corner, x equals the square root of t. And that's, let's see, since I drew that, that'd be 1, 1 right there. So something like this. Okay, and so that, again, is time versus the x value. Of course, my final graph, which I should have drawn in red, but I'll use this, x versus y. You can see that I can, the y value for this guy right here is matching the vertical axis here, but the x-axis for this guy is not. So I'm going to go ahead and rotate this 90 degrees to the clockwise, basically, to the right, where initially it would look sort of like that. Just pretend for a moment I did that right. And then I'm going to flip it about the new x-axis, but I'm going to flip about the horizontal axis. So what I should get is the following. All right, something like that. And again, this is the x-axis now. And this is my time axis now. Now, time equals 0. I'll go ahead and use red to graph this. Time 0, the x value, time 0 is 0, and the y value is 1. So let's just plot that. And then as time goes forward, the x values increase and the y values decrease. And that's what is tough. As time goes forward, the x values increase. So my x values are going this way, my y values are going this way. But again, that's why I say it's very difficult to do this if you're going to do the graph. The x values don't increase super fast. So as time goes forward, the x values, like if I'm here and in here, these are the time values. The x values don't really jut over as quickly as the y values fall. So it's the x values, the y values are going to fall faster than the x values are increasing. So it's going to look something like this. And that matches what we have there, but the table actually gives a little more accurate of a graph. It's also easier to understand. So it's your choice, but there are times when graphing really does help out. So it's a skill that you need to be able to practice. All right, let's see what we have up next. Okay, so here's another trigonometric relation. It's a parametric curve. X is equal to sine of theta over 2. Y is equal to cosine of theta over 2. They're telling us to do this just from negative pi to positive pi. Now, if I were to eliminate the parameter here, that's actually not too terrible to do because sine and cosine are related to each other by the Pythagorean identity. Sine squared of theta over 2 plus cosine squared of theta over 2 is equal to 1. Therefore, x squared plus y squared is equal to 1. So this is, again, the graph of a circle. However, be very careful with this one because notice the domain, for my time here is negative pi over 2 to or negative pi to positive pi. So let's go ahead and at least, graph the circle, and then we'll clean it up. So it is going to be a circle of radius 1. I'm just going to, yes, it's going to be a horrible circle. Much better in class with circles than I am on a piece of paper. And so what I'm going to do is now consider building a table of values to kind of see how it cuts itself out. So again, time versus x and y. When we're at negative pi, so let me write that in here, negative pi. We're at negative pi, we're at sine of negative, the x value is sine of negative pi over 2. Sine of negative pi over 2 is actually negative 1. The cosine of a negative pi over 2 is 0. And I'm going to step forward, so let me mark that point here, by the way. So x equals negative 1, y equals 0, right there. And now I'm going to step forward a little bit, just not too much, just a little bit. Let's go to negative, let's see, we're at negative pi. Let's go to negative pi over 2. So when I plug a negative pi over 2 into the sine, I get the sine of negative pi over 4. Well, the sine of negative pi over 4 is a negative 1 over root 2. The cosine of a negative pi over 4 is actually 1 over root 2. And so my x value is still negative, my y value is positive, so I can see that I'm actually going in this direction. That's how I'm carving it out, just like this. And now let's just go ahead and throw in a couple more values since we can. I'm going to go to 0, and then pi over 2, and then pi. Okay. So for the sines, sine of 0 is 0, sine of pi over 4 is 1 over root 2, and sine of pi over 2 is 1. For the cosines, cosine of 0 is 1, cosine of pi over 4 is 1 over root 2, and finally cosine of pi over 2 is 0. So let's see, let's plot these points here. So we'll be at 0, 1, so we're going all the way up to there. And then by the time we get to time pi over 2, we're at 1 over root 2, 1 over root 2, which is probably right about there. Continued along our path. And then we finally end this path at 1, 0. This means that this curve does not include any of the stuff below the x-axis. This is all this curve is just this upper part of the circle. So be very careful, just because you're going from, notice the period of this rotation here is actually at 2 pi, and yet we only went through half a circle. It's because we're going at half speed. These angles here are half speed angles, so you're not going to carve out the entire circle. So just be very careful about that. All right, what would calculus be without a sinh or a cosh? So sketching this, this is kind of just thrown in here just for fun. The relationship between cosh and sinh is that cosh squared minus sinh squared is equal to 1. So that means that we have y squared minus x squared is equal to 1. That will be a hyperbola. And hyperbola is actually, maybe this is not such a simple example, because hyperbolas have 2 branches. So this one is opening in the y, because the y is a positive value. It's going to open both this direction, and normally, trying to get it symmetric here, but it's not going to look symmetric, normally this way as well. However, something you need to know, if the y values are defined by cosh, the cosh is equal to e to the t plus e to the negative t over 2, which is always positive. In fact, it's not ever equal to 0, it's just always positive. So that means that the y values are always positive. We don't have the lower branch here. Okay. And now what you can do is you can actually figure out what the direction of travel is. And this one's kind of unique as well, now I'm thinking about it. Let's build a table, t versus x versus y. Just chicken scratching it out. Time of 0, you have sinh of 0. And if you look at the sinh of 0, that's going to be actually 0. And cosh of 0, if you look at that right there, cosh of 0 is going to be 1 plus 1 over 2, or 1. So we start here. All I need to do is grab one more value, and I'll be able to see the direction of travel very easily, actually. And so what you could do, again, is note this e to the t minus e to the negative t over 2. If you plug in a positive value for time, let's say time equals 3, you'll get e cubed minus something very small over 2. So the x values are, that's going to be positive. The x value will be positive, and the y value is going to always be positive. So you're heading in this direction as time goes on. If you were to try a value like negative 3 into the x equals sinh of t, you'd have e to the negative 3, which is a very small value, minus e to the negative 3, or e to the 3, which is a large value. So small minus large, that's going to be negative. So my x values are going to be negative for negative time values, and my y values are always positive. So for negative time values, I'm back here. So negative time values lead to positive, so you can see the direction of travel for this curve. All right, let's see what else we have. It's a good example of something that looks as though you cannot relate out or eliminate the parameter, but you actually can here. That's x over 5 is equal to cosine of t. And that's y over 2 is equal to sine of t. And because we know that cosine squared plus sine squared is equal to 1, we know that x squared over 5 squared plus y squared over 2 squared is equal to 1. And if you remember your good old pre-calculus, that is the equation of an ellipse. And so if I want to graph that, the major axis is, because the larger denominator is the x-axis. So 1, 2, 3, 4, 5. 1, 2, 3, 4, negative 5. The y-axis is the minor axis. So I'll initially connect those up. Can't say that this is exactly what it's going to look like, but we can at least hope. Something tells me that my y direction values were much more, or the positive x values were much more elongated than the negative x values. Sorry about that. Okay, so now let's find the direction of travel. We're going from time equals 0 to time equals 2 pi. So t versus x versus y, time equals 0. Cosine of 0 is 1, so that'll be 5 times 1. And then sine of 0 is 0. Time equals pi over 2. Cosine of pi over 2 is 0. Sine of pi over 2 is 1 times 2 is 2. So I can easily see right now that I went from 5, 0 all the way to 0, 2 in time pi over 2. Now, actually, this speed will maintain throughout, so it actually will continue from that. This will be time pi, and this will be time 3 pi over 2, and we'll be back here at time 2 pi. So that's a good graph of that parametric equation. Now, this next example, I got a little lazy. I just stole it from my lecture, but this is just going to use a little bit of technology to see how technology can be used to help us sketch some really interesting parametric curves. Let me go ahead and pause this and get my WinPlot ready. It's not completely ready, but I just want to showcase a few things here. So what I'm going to do is graph, let's see, cosine of e to the t will, or cosine of e times t will be my x value. So here's how this works. Here's the WinPlot. I'll just go here to Parametric. And I'm actually sort of going to cheat on this. I'm going to write cosine. It's not cheat, actually. I'm making it more interesting. Cosine of e times t times and then a. And the reason why I'm using a is because I want this to draw out so we could see it in action. So normally you wouldn't do that. You just say cosine of e times t. But again, I want to showcase how it draws out. And then let's see what else we have. Sine of square root of 3 times t. So let me go ahead and put sine of the square root, sqrt, of 3 times t, and again times a. I want this, I'm going to do this from t equals 0 to 200. There's a reason why. And I don't want to actually graph this yet, so I'm going to press pause to set up one other thing. I want to set up what A is going to do. Actually, maybe you should be able to see what A does. So I'm going to hit OK here, and I'll close this out. And let's see, I'll go to Animate, Parameters, and I'll have A go from 0. So notice how it says 0. I'm going to set left there. And I'm also going to highlight this and hit 1, and I'll set right there. Okay. Last thing I'm going to do is I'm going to set slides here to be 200. Let me close this. And I'm going to change my window to be a 1 by 1 window. So I'll change set corners here to be a 1 by 1. So -1 to 1 and -1 to 1. Apply. And you see it automatically filled in, but I'm actually going to now go to the parameter A here. Just do this. And what it's going to do, that 200 slides, is it's going to go through and cycle through 200 slides. So here we go. I'm going to auto cycle here. That is way too fast, so I'm going to slow it down so you can see this drawn out. And I'll slow it down even further. So that is a look at this parametric curve. I wait, and I'll have it go through one more time completely. Maybe I'll speed it up so we can get to the beginning of it. And then I will, at the beginning, reset and really go slow. So you can see it graphing out. You can see how this curve is graphing. Very, very neat. And this is that parametric equation that we just saw. X is equal to cosine of e times t, and sine is equal to square root of 3 times e t. Or maybe it's square root of 3 times t. Maybe that's what it was. So anyway, that's what it's graphing out from t equals 0 to t equals 200. All the rest of it was me just setting up this animation, but very cool. So this is, again, not a function of x, nor is it a function of y. This is a tartan pattern, is what they would call this. Let's stop that. So for our final example, this very basic example, suppose that somebody hands us a function and we want to write it as a parametric equation. The easiest way to write this as a parametric equation, we're going to let x equal time and y equal time cubed plus time plus 2. Well, now you can easily see that works out. But why would I ever want to do that? And the reason why is because f inverse, when you find the inverse of a function, you're basically swapping the roles of x and y. And that's literally what we're going to do here. X will be equal to t cubed plus t plus 2, and y will equal t. That's it. So very nice to be able to find a graph of an inverse function. Now, again, these, well, I don't want to say again, but the inverse may not be a function of x, but that's okay. I can at least graph the functional curve, the inverse function curve. Not that it will actually be a function, so I should say the inverse curve. But you can easily find inverses this way.